Okay, so the last time we talked about the product and the universal mapping property that it has. And what it does is it sort of lifts bilinear maps. You've got some kind of bilinear map from G to C. So remember that's basically an R module homomorphism in any coordinate when you freeze the other. This is the canonical bilinear map. We checked last time this is bilinear. So if you've got bilinear map from A cross B to C, then this lifts to an R module homomorphous G bar from the tensor product C. And there's actually power in this because, as you've seen, we built the tensor product, and you saw what an unholy mess was, right? I mean, it was a free abelian group on the set, and then we imposed relations on it. And so, if I just walked up to you on the street and said, "Hey, build me a homomorphism from here to here," then the first thing you better worry about all kinds of stupid shit, like, oh my goodness, my domain is coset, so all of a sudden I've got to worry about what I'm finding this. It's really obnoxious, right? So this is actually a powerful theorem because what it says essentially is without having to check anything, you can take a bilinear map, which is usually easier to wrap your head around, and poof, turn it into a homomorphism. You don't have to check well-definedness, you don't have to check homomorphism, which is certainly a good situation. So let's prove this and do the heavy lifting for once. It's really not that heavy. So our burden here is to build this homomorphism G bar. So we'll say that F free abelian on A cross B, and K is subgroup described in construction of so is that subgroup generated by those certain ordered pairs, right? So and well, let me just say induces a homomorphism I'll call it star, I guess, from F. This is why we needed the free abelian group business, right? Because this map right here is bilinear. Just forget about that, right? I mean, remember, we were free abelian on this, so this bilinear map that goes from here to here is a function. And what happened with functions and free objects? This induces a homomorphism from F to C. Right? That's because F is in fact free. And as G is bilinear, G prime must take every element of K to zero, right? Let me be a little bit more specific. G takes every element of K to zero. Why is this? Well, because remember, uh, since G is bilinear, this generator of K is taken to zero. Why? Because the bilinearity makes this collapse to zero element here, right? And so, what does this mean? Well, this means that it means that K is contained in kernel of G bar. And so this induces say G bar from F mod K to C. And of course, F mod K is the tensor product. And we have the property that G iota, G bar, iota of AB is G bar of A tensor B, which is G of AB. So, Gi is G. So that's the first part. Now, on the other hand, if we have H we have, because this is supposed to be unique homomorphism. H from B to C, I'm sorry, H from A tensor B, C, is such that H iota is equal to G. Then you look at H of A tensor B, this is equal to G of AB, which is G bar of A. Okay, so what can we conclude from this? Well, this means that H and G bar agree on all tensors. But everything in the tensor product is a sum of tensors. And so if they agree on all single tensors, they have to agree everywhere because these are both R module homomorphisms. So we have gotten the fact that this homomorphism is unique. The last thing that I left out was the statement about the tensor product is unique of isomorphism. see if you can check that. Okay, any questions? Okay, we did a corollary to this last time. Let me quickly, I wanted to discuss the corollary just a little bit more than I did. So I've stated this before, so I'll be brief. Suppose F goes from A prime, B goes from B prime, R multiple morphisms, and P. Then there exists a unique homomorphism which I will call F tensor G from A tensor B into A prime tensor B prime, such that F tensor G of A tensor B equals F of A tensor G of B for all A and A, B. Okay, so I wanted to bring your attention to this for a couple of reasons. Number one, I wanted to introduce to you this notation. This is sometimes called the tensor of homomorphisms. So you've got these separate ones that go from A to A prime, B to B prime. So you can kind of tie it together with this. We call this the tensor of two homomorphisms that acts as well. Tensors. Let me point out again that once so we know that this is a homomorphism. Well, let me show this. This is a homomorphism. Once I tell you what it does on tensors, you know what it does everywhere. Because this is, once you know this is a homomorphism, the sum of tensors, knowing what it does to the generators is good. So how do we show this? Well, let's make the following binary map. This is the way I always attack all these kind of problems here. I want to define a bilinear map. Let me call it something creative like H. How do you suppose I want H to work? What's the best way to get a bilinear map from A tensor B to? Remember, folks, this is math class. Better make it easy. So take an order pair here. I've got to get some element of each product here. Well, how about a single tensor? Because hey, that's easy. First coordinate, second coordinate. I think everybody would have to agree that when my input is AB, my output is an element of A prime. I've got the here's my canonical map where I have AB to A tensor B, and this goes to I guess really if I'm being Mr. Good Professor, I should probably do this. I'll do it first with art. This is probably not a big surprise to anybody. What happens here, if I freeze the B, this is equal to F of A1 plus A2 tensor G. And of course, F was an orthogonal homomorphism, so I can strip that out. Now I can distribute the tensor. This is F of A1 tensor GB plus F of A2 tensor GB. And this is, of course, H of A1B, H of A2. So it's linear, or it's an abelian group homomorphism when I freeze. Second variable, I will leave the proof for the second to you. It's the same thing. Right? And if I have R, this is R, F A, tensor GB, which equals R F A, tensor G8, which is F A R, tensor GB, which is actually, if I take you over to the other side, F A tensor R GB, which is F A tensor G R B. And this bit is H of R A B, and this bit is H of A. So it works with standard multiplication, so that's good. So this is bilinear, as promised. So by this mapping property of the tensor product, there exists a unique F, which we christen as F tensor G. It goes from here to here. Such that F there we go. So there's okay, any questions? Let me use a special case of the corollary here. So suppose let's suppose F B and D is R mod. I could do anything on this here, but F A B induces F bar at the identity from from A tensor D into B. And by this corollary, I know how this acts. I know how this acts on tensors. And once I know how it acts on tensors, I know how it acts on everything. F tensor 1D of A tensor D is F of A. Right, basically the identity on the second entry. So if I have a homomorphism, F from A to B, then this induces a homomorphism from A tensor D to F to B. This might seem familiar because then we do something similar on. Right? And that's exactly where we're going with this. So theorem 685. If D is an arm, and tensor is exact. I'm sorry. Right. Home for left exact. Tensor is right exact. And what I mean by that is if A, B, C, 0 on what's F and G, that, then so in other words, home is good with one-to-one stuff, right? Tensor product is good with ontos. What do you- almost- Does anybody want to ask why? There are, in home, there were two versions, right? Home, when you let the first coordinate be stable, then it was covariant. If you let the second coordinate be stable, it versus directions matters, right? This doesn't happen. And in fact, whether you tensor D on the left or the right doesn't matter. Before I prove this theorem, probably seems to be obvious which way this is. But how much you do this? You think of a bilinear map that goes into B tensor A. Swap, that's right. This was up here, B tensor A. check that this is bilinear, right? It's not too difficult, right? So I get a homomorphism here to here, right? See if you can have, let's say, do the same, play the same kind of game in reverse here, right? So you can start here with B cross A, go here, although this is a swap, you can do a B cross A, do a bilinear, see if you can show that this is actually isomorphism, and also those the other way is an isomorphism. So I don't want to spend too much time on that because it's not difficult to show, but that's one of the reasons why you get something different with palm in two different variables. But tensor product, I can tensor on the left or the right, and then what you get is isomorphic. Let's prove this. Right. Okay, so let's go through the proof of this. Okay, we already know from the work that we've done that what we have is these are bona fide R model homomorphisms. So that's good. Okay. How do I know that G tensor D is on? Well, this one's not too bad. Be an arbitrary. Let's see what we're looking here. What do we know about the map G? G is on, so there exists B, such that C is G. So C tensor D is GB tensor D, which is G tensor 1D times the tensor B tensor D, or operating on B tensor D. Right? So what does it show? Well, what it shows is every single tensor is in the image of G tensor 1. Right? Since C tensor D is generated by all such tensors. C tensor D is contained in the image of G tensor. So G tensor 1D. So tensor is really good content. Okay, what else do we need? We need the image of F tensor one D containing kernel of F tensor, I'm sorry, kernel of G tensor. This is also pretty complete. Uh, 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 If we look at well, so let's just look at the composition of the maps of F tensor one and G tensor. So F tensor one, this is what an arbitrary element of A tensor D looks like, it's a sum of tensors. This translates to sum of F A I tensor D I. That's how the homomorphism works in tensors. And this is the sum of G F A I tensor D. Well, what happens when you do F and G? Well, you get zero because the original sequence was exact. So this thing is zero as the image of F is in kernel of G. So this is the sum of zero tensor DIs. Because we already know zero, when you tensor anything, zero. So it's a sum of zero tensors and it's so let's wrap it up. So image of F tensor one is contained in the kernel of G tensor. Okay. Good to go on that. Finally, I want to show that the kernel of G tensor 1D containing an image of F tensor. And I'm going to do this sort of more globally as opposed to element wise. So what I'm going to do first is I'm going to consider this projection map from here onto P tensor D, my image of F tensor. And I'm going to call that pi. So this is actually a similar argument to the original proof of the tensor product. So and this is just a projection that you would think of. It takes any element here just to that element plus coset or plus m the coset that plus image of F tensor 1D. There also exists a homomorphism. from D tensor D here. Um, and the way this one is going to work is oh, now, again, I'm just telling you how this works on tensors, but if I tell you how this works on tensors, I'll tell you how it works everywhere. Where this is equal to GB tensor. More dramatically, B tensor to 1D. In other words, when I go here and here, on tensors, when I go from here to here, it's the same thing as going this way. By the way, how do I know I have this homomorphism? Because what do I know already what I've done so far? I know that the image of F tensor 1D is contained in the kernel of this map, right? I've already shown that that's a previous step. Since the image of this is contained in the kernel of this map, then this is basically, this is the same thing. This induces a well-defined map here because of the fact that what you're modding out by is contained in the kernel of this. That's why it's well defined. And so basically you just take this trip away. Everybody okay with that? What we really need to do now is to show this thing is, I'm missing one. Right. And that'll get us that, well, let's just show that and then we'll do the end game. How are we going to show that this is an isomorphism? Well, I'm going to build this using the what I know about the mapping properties of the tensor product. So what I'm going to do to show that this is an isomorphism is I'm first going to consider, I'm going to call eta into the tensor in my image of F tensor 1. So as you might expect, what I'm doing here is I'm trying to set up to get a homomorphism from the tensor product. This is actually a good illustration, I think, of why this business with bilinear stuff works so much better. How am I going to get here, right, and do a bilinear map? Well, I am going to take an arbitrary ordered pair like this, and I'm going to assign it, right, I'm going to assign this to pi b tensor where t where such that you can. Now this should probably set off some warning lights here. So how do I make this bilinear map work? I read my order of pair here and I assign it to pi of b tensor d. I know where I get D. It's from here. Where do I get B? I get it from looking at something that goes to C. What's the alarm bell should be going off here?
There could be a lot of things that go to C.
There could be a lot of things that go to C. This may not be well defined. So let's suppose that, for example, G of B1 is C. Okay, so let B1 be another preimage, B and B1 are preimages. This means G of B minus B1 is equal to 0, right? Because they both go to C, which means B minus B1 is in the kernel G, which is the image of that, using the exactness of the original sequence there. So what can I do? Well, there's some A and A such that A goes to B minus B1. And so, sorry, F A tensor D is in the image of F tensor 1. Agree? And so if I look at pi, right, when I look at pi of f of a tensor d, that just projects this coset, f of a tensor d plus image of f1d. But I already know that this thing is in here. So this goes to the 0 coset, right? And so how can I leverage that? So if I look at pi, this is pi of f of a plus b1 of b. Sorry. Right, because b is f of a plus b1. Now what these tensors out, this is f of a tensor d, and this is b1 tensor d. Now pi is of course a homomorphism. So this is pi of f of a tensor d plus pi b1 b tensor d. And this is 0. So this is how b1 tensor d. So pi of b1 tensor d is pi of b2 tensor d. So in particular, theta is 12 pi. Because independent of the preimage choice, I got the same outcome. My opinion. Okay. So, now that I know this is well defined, it's easy to check that this is bilinear. Because if I replace this with C1 plus C2, that involves replacing this with B1 with B2, it distribute the tensor bilinear, and this is when you first there, and so forth. Everybody okay with A to B bilinear. So A is bilinear, so there exists a unique A bar from C tensor D to B tensor D. Image F tensor 1D. Such that eta bar C tensor D um, is equal to pi B tensor D. So what can we conclude from this? So given any generator, C tensor D, then what we have is this is equal to which is equal to G of B tensor D which is G tensor 1 D, which is actually C tensor. So when I do eta bar, then tornado, I get the identity. Now show the other one is similar. The identity on sort of right, B tensor D on the image F tensor 1. And so in particular, we have an isomorphism. From this. Okay. Any questions? Let me give you, yeah, just the right amount of time, but let me give you one last theorem, without proof for now. And we'll talk about it next time. And then, class. Well, I want to do some more computation. Theorem. 686. The R module. If the short exact sequence 0, A, B, so this is similar to home in the sense that we get if the short exact sequence splits, then so does the tensor. So we use tensor. The- So if you actually have a split exact sequence, then you get a split exact sequence, after tensor. You might ask if you have a short exact sequence, is it short exact? And the answer is in general, no, it probably doesn't always behave well on one maps. We'll talk more about that next time. Any questions? Any questions? Well, think about the map for today. I hope you'll have a good weekend and I will see you on Monday.